In this webinar, we're going to talk about LoRa and LoRaWAN and why it's a good solution to a long-standing problem in IoT and specifically Ag IoT in terms of getting sensor data up to the cloud without having to have huge amounts of power available. We're going to look at how it achieves that and how it outperforms some of the other sensors, and then we'll dive into LoRaWAN and see how you can build a network of things. So to get started, let's just go ahead and introduce some terms. We've got LoRa, of course, and LoRa stands for long range. It's a proprietary standard owned by Samtec. They have a lot of circuit IP available to other vendors as well. So Samtec makes some LoRa radios, and so does some other vendors. They make hardware with LoRa, Samtec LoRa IP embedded in it. So you don't have to just get your radio from Samtec, but it is proprietary and owned by Samtec. So that's a little bit of a disadvantage, but it's a very good low power radio design. And it has a really wide area of broadcast. It's a 900 megahertz radio, and it can go up to 5 miles and more sometimes. But it's just a radio. It just sends bits from one radio to the other. It doesn't really know how to build a network of things or how to build a system that works well together. And that's what LoRaWAN solves. It's a protocol and a system architecture. It's an open standard. It's maintained by the LoRa Alliance, which is a nonprofit industry consortium. And essentially, it builds this network of things, and it describes how they're supposed to communicate with each other so that stuff is compatible and interoperable. There are lots and lots of vendors of LoRa and LoRaWAN hardware. Here are just a few good examples from some larger companies. They offer lots of products, from gateways to sensors, from sort of development boards to really hardened products. So if you want to use LoRa today, it's a mature technology, and there are a lot of solutions available for you. But we should stop for a second and ask the question, what's the end game here? Really, what are we trying to solve? And the problem that we have needs a lot like they're spread out over a long range of area. So a range of the radio is important. There's very little power available. These are usually battery powered or solar panel powered, and you can't spend a lot of your time going out changing batteries. At worst, it needs to be sort of an end of the year, once a year kind of operation. You're going to have lots of them. That is, if we correctly deliver on the goals and the promises of IoT, you're going to have sensors scattered all over the place, all over your farm. So they need to be cheap so that you can buy them all. Those are kind of the obvious requirements that everybody's talking about. But there's some other side effects that are important and really what makes LoRa fit well. One of those is that most of these sensors, they don't have much data to send. Think about some of the possibilities. Maybe a soil moisture sensor. It just has a few numbers to send, maybe only a couple times a day. It's not very much data. Even smaller, a door sensor that can tell you if the door is open and closed, so you can make sure you close the freezer holding your cow's antibiotics before you left, and you don't lose a whole freezer full of antibiotics. Or maybe it's a wrist bracelet on a cow that's sending out biometric data to check for sick cows. That one maybe has more data to send. Maybe it's tens of numbers, but still doesn't need to be sent very often, maybe just once an hour. Temperature sensors, GPS trackers, weather stations, all these things are examples of stuff that don't have many things to send, just a few numbers, and just a few times a day. So these two things together are really what LoRa buys into, and then says, because we only need to send a small amount of data, we can do much better in these areas up here. And then the last thing is a purchasable network. And what I mean by that is, as a producer and you buy and install sensors, you don't want to also have to figure out how to deploy the LoRaWAN network and how to move the data from all your gateways back to the cloud, to the producers that need, to the consumers that need it. Want all that infrastructure to already exist. It's not that you can't do it. It's just that it's so out of your normal mode of operation. It's better if you let somebody else more specialized in that area to do it for you. It's the same idea behind you purchasing cellular connectivity from AT&T or Verizon or a company like that to download RTK corrections on your planter. You could install a differential GPS unit on your farm somewhere and set up your own radio. It would be free, but it would be a lot of extra work that may not return the value for you. You'd rather just pay for access to the cellular network. I think it's true that the producers want to pay for access to this IoT network. And when we do that, that's really when we'll see full-scale, broad adoption of IoT sensors in ag, at least at the farm level. The good thing is LoRaWAN helps us deliver on this promise too. We'll see all that as we go along. But before we dive into LoRa, we should spend a few minutes trying to understand why not something else. Now, this is my hot take on what is good and bad about the different technologies. And it's really just a big summary of what Yang showed you some webinars about a few weeks ago in one of the earlier webinars. And the idea is really just cellular is really great for high data rate things. You want to watch videos on your phone, it's a perfect solution. But it's not very good on power. It's not very good on cost. It's designed to that most people would only have a handful of these, not thousands of these. And it's good in range, at least from a network perspective, because the cellular network has lots of towers. So you pretty much can use it wherever you want, except when you're out on the field, which might be a disadvantage for cellular as IoT, is that the very, very rural parts, like the cornfields themselves, may not have good cellular coverage. Wi-Fi is a great solution. It's extremely cheap because it's so ubiquitous. It's in everything. It's got really high data rates, but it doesn't have good range and doesn't have good power. It doesn't fit IoT very well. Category M1 and narrowband IT, these are sort of derivative technologies from LTE, and actually most LTE carriers like Verizon and AT&T, for example, also support either one of the Cat M1 or narrowband IoT protocols, depending on where you are in the world. They're both actually decent solutions to the IoT problem, and I don't want to bash them too much, but I would say that they still fall down in some of the categories that LoRa can do better in, but they solve a different problem. So, for example, Cat M1, it's kind of medium power, medium range, medium data rate. It's this happy middle. Maybe you have a video camera you're trying to send video data from, but you need it in a more rural location. M1 might be a perfect match of kind of a little bit faster speed, but still needs some decent power. But maybe if you have a video camera, say in a barn, you might have power there. So it solves this problem where maybe there's power but not internet. Narrowband IoT gets a little closer to LoRa in its ability, but I would say it still is a little bit higher power than LoRa. It's a good solution, and it should be considered even in situations where we're considering LoRa. Lastly, I include Bluetooth. Of course, it's great for your headset to your phone kind of things, but it's not so good for IoT because of its range. So then lastly, we get to LoRa, which of course has lots of green checkboxes, but I want you to notice something. It's traded something. In fact, all these have traded something. When you see a couple of green boxes, the other boxes are red or yellow. And that's because essentially physics sort of demands that if you're going to have high range, then you're going to have to give up on power or data rate. Or if you're going to have high data rate, then you're going to have to give up on range and or power requirements. They sort of trade off each other. You can't sort of be good at all of them. And so what LoRa has done is decided to trade off data rate to an extreme. It's extremely low, but that makes it really high range, really low power, and because they use some simple technologies, really low cost. But we have to ask the question, can we have really low data rate? Well, we've already talked about in the last slide that the low data rate per sensor may not be a problem. Capacity, though, is a problem. If I have one radio link that's very slow, then I can't have many devices talking. There's just not a lot of bits available to send. So LoRaWAN comes to our rescue here. It takes LoRa's low powerness and creates capacity through an intelligent network architecture. And actually, it's probably not fair to compare LoRa to, say, Cell or Cat M1 or narrowband IoT, because these are more networks of things rather than just radios, in the same way that LoRaWAN is a network of LoRa. And so, to be fair, we should compare LoRaWAN to these things, and we will do that in a second. But before we do that, I want to talk about how slow LoRa is. I really want to get into your mindset, because it's important that you decide and ensure your application is a low enough data thing to use LoRa. Because if you have a high data rate need or even just a moderate data rate need, LoRa may not be the answer for you. So to sort of get some intuition of what that means, we'll look at some used applications here. So this is like, say, audio streaming, if you go to Google Music or something like that. And it's like half a megabit a second or 500 kilobits a second, 500,000 bits a second. You watch a YouTube video, kind of normal quality, it's at 2 or 3 megabits or 2 or 3 million bits a second. You watch a 4K video on YouTube, you're talking about 30 or 40 megabits a second. And you think about internet providers that you might have to your house, or maybe it's a cable modem style thing. A lot of times they'll say you get a gigabit, and of course we know we always get something a lot less than that in practice, right? I'll put it somewhere here right around 500 megabits a second. Or maybe you're in rural America and you're on DSL. You're probably looking at a couple of megabits to say 10 megabits a second. Good enough to watch video, probably not good enough to watch 4K. Then we can look at wireless networking options that are available. In your house, you probably have Wi-Fi, let's just say 1 gigabit per second. Kind of depends on the installation quality, the quality of the radio, of the Wi-Fi radio, and the clients you have, but it's achievable. It's usually good enough to get the full use out of your cable or DSL provider. You have your 3G, 4G, 5G cellular access, and 3G is kind of like DSL, 4G is kind of like cable, pretty close, and 5G is kind of like future. And really, to be honest, to get these types of speeds in 5G is still pretty rare and just in very small selected areas. Maybe it's coming, but even today it's kind of up and coming. Then you have your traditional side of IoT networks, Z-Wave, Zigbee, Bluetooth LE, low energy, all these types of networks. They tend to run around 100 kilobits a second, close to good enough for audio. And then you have LoRa all the way down here at 10 kilobits a second. And actually you have LoRa for real, most things running even slower than that, maybe just a kilobyte or two a second. To be clear and show you a reference, dial-up internet is 56 kilobits a second. It's right here. And so most LoRa sensors are running at a tenth of the speed of dial-up. Like we said, this is probably okay for a lot of our applications, but we need to be really careful. If you have a data requirement that is too fast for dial-up, it's certainly too fast for LoRa. And you should be looking for other solutions. It's where LoRa gets a lot of bad rap. It's so slow. It's true, but it has really good applications still. So why use LoRa? Well, because we can solve the capacity problem. So we can have a really low power long range radios that and have sensors that only move small numbers of bytes and still have many sensors. And we can do that with LoRaWAN. LoRaWAN just uses LoRa like we talked about, but it uses it in parallel a whole bunch of times. So in the United States, the ISM band that LoRa uses is the 900 megahertz region, and there's 64 LoRa channels in that space. What that means is for a full-size LoRaWAN gateway, it can talk up to 64 LoRa sensors simultaneously. This is like your radio stations and your FM radio. They're all running at the same time, and you can kind of tune into the radio you want to hear, but they're all running in parallel, except that the LoRaWAN gateway is capable of listening to all 64 radio stations at once. In fact, there's even 8 higher bandwidth channels sitting on top of these 64 lower channels, and these can run at a faster bit rate, but require more power to do it. And since it's a higher bandwidth, there's only space for 8 of them. Turns out after some crafty waveforms that LoRa uses, you can actually use these 8 simultaneously as all 64. So you really have 64 plus 8 channels to send data over. And that's the mechanism in which we increase capacity. We have lots of parallel slow LoRa links. And it's a trade-off that most of these types of IoT networks are using. You haven't really solved the low power. What you've done is set up a situation where your gateway, where there is internet and power, has high power needs. They have to listen all the time and process 64 different channels, so that the remote sensor that doesn't have a lot of power can use just one of those channels in a very simple way. So you have low power at the client and high power at the gateway where there is infrastructure. Similarly, to send data down to a device, there are 8 dedicated high bandwidth channels. Typically, data doesn't need to go down; it only needs to go up, and so they've reserved most of the bandwidth for uplinks, capacity for uplinks rather than downlinks. If you like to see get some intuition, if we had just a modest 8-channel gateway, which is kind of the smallest that LoRaWAN allows, so it's just 8 of these 64. That gateway can handle over 100,000 messages a day if it's used at a reasonably full capacity. And if you had sensors or devices that sent each 10 messages a day, that's over 10,000 devices per small LoRaWAN gateway. If you scale up to the full-size gateway, like Jack will show you in a little while, you can have hundreds of thousands, if not millions of sensors under just a handful of gateways. So LoRaWAN really does solve the capacity problem. So like I said before, summarizing, we're good on range, we're good on power, we're good on cost. And if we add WAN to LoRa, we're good on capacity. We're still really bad on data rate, but our application allows for it. It's a perfect match. for ag and IoT. There's some catches though. The amount of power that you use is certainly a function of rate. LoRa does a lot to be low power by itself. It uses something called chirp spread spectrum, which means that you can build really energy efficient amplifiers, which is the biggest consumer of power in a radio. It has time synchronization that allows you to turn on and off really quickly, so that there's no wasted time. When you turn the radio on in its high power mode, you can send your data immediately and turn right back off. So these things add up to lower power by design. But really the low power in any of these types of wireless systems is the fact that the sensor or the device isn't on very much. It uses very little airtime. And in fact, LoRa really encodes that into the standard. It defines 3 different classes of radios. There's class A, which essentially says it's always asleep until it wakes up to transmit. Once it wakes up to transmit, it will wait about 1 second usually, and then listen for a reception, and then wait another second, and then listen for a reception. If the gateway wants to talk to that device, those are the only 2 opportunities it has to talk to it. Otherwise, the sensor's going back to sleep forever until it's ready to wake up and send data again. This class, and this of course is the lowest power mode of operation. The sensor is entirely in charge and it only uses power when it wants. There's a class B device that works similarly, except it also then wakes up periodically. These are good for actuators. Say maybe you have a irrigation system with a relay on it and you want to be able to use LoRa to turn on and off the irrigation system. Maybe you program the LoRa radio to wake up every half an hour to check for a message, and that gives you the ability to turn on and off the irrigator from remote at half an hour increments. That also lets the actuator not be on very much, and so it saves its power. And then finally, class C devices, they're just always listening. These are more like gateways. These are high power things. These wouldn't be sensors. It's the other side of LoRa, that side that has all the energy usage so that the A and B class sensors can be low power. And then I'll say it even gets slower than what we've talked about if you need more range. So really LoRa trades speed for range like all radios do, except it gives you the ability to control how it trades it. And the critical idea here is that essentially the longer I send a set of bits, the more time I take to send it, the easier it is to receive on the receiving end. And therefore the longer you can go, because as that signal quality degrades from the range, it makes up for it by transmitting it for longer. To see in a little simple example, here I'll let you listen to this Morse code. These are beeps, and it's embedded in pretty strong background noise. And these are running at sort of quote unquote full speed. And it's a little difficult to hear. And then if I go over to the long beeps and boops, then what we can do is play it. And it's the same beeps and boops, they're just longer, with the same background noise. It's a lot easier to tell what's going on. It's a lot easier to detect what the bits are. And therefore, you can go for a longer range. But because we're sending each bit for a longer period of time, we can't send as many bits in a second. So LoRaWAN has this defined in it as well. We have these different data rates. For example, if we have data rate 0, we can only send 980 bits a second, but we can send it almost 5 miles with one radio. If we pick data rate number 3, for example, we can be a lot faster, 5,470 bits a second, but only for 1.25 miles. And so we get to trade this off. Now keep in mind this data rate 0, it's going to use more power because it takes a lot longer to send the same bits as data rate 3. But we can go further. LoRaWAN has the ability to do adaptive rate control, which basically means the sensor and the gateway work together to figure out what the right data rate is so that the power is minimized and the receptions are still strong. We won't go into those, but that is part of LoRaWAN. Okay, so now we've kind of talked about LoRa and how it works. Let's look at the architecture of LoRaWAN. And it looks something like this. These are sensors. You know, you got your temperature sensors, your soil moisture sensors, maybe your irrigator control, things like that. This represents a LoRa gateway. And the LoRa gateway is connected to what's called the LoRa server through a pre-existing link. This could be cellular backhaul, it could be a point-to-point Wi-Fi link, it could be fixed wire internet, maybe it's fiber or some sort of already existing internet service provider. Anyway, these blue lines are somehow already existing high-quality links. The only thing that's LoRa is from the sensor to the gateway. The gateway doesn't really do anything. It just takes the message that's sent from the sensor and it checks to make sure the packet was received correctly. And if it was, it just forwards it uninterpreted to the LoRaWAN network server. The LoRaWAN network server then looks at it, validates that its packet's allowed, decides whether it's an application data or if it's a message that's part of LoRaWAN communicating with itself to control the network. In this case, it's application data, so it sends it on to the application server while including a sort of check saying, yes, this is a real valid packet. The application data server can then do whatever it needs to do to open that packet, decrypt it, make sense of it, and then sends it to the end user or application that needs it. Similarly, if the application needs to make a response, it sends a response back to the application server. It packages it up to a LoRa package. The network server determines which gateway to send it to, asks the gateway to transmit it back down to the device. Of course, if we were to say a Class A device here, this would all have to happen within 1 or 2 seconds to be sure that the response makes it back to the client. You can kind of split this picture into 3 different boxes. There's sort of the device owner. These are the producer, the grower, whoever owns the sensors. There's sort of a trusted vendor. They're the ones who created the backend, the application that the producer is trying to use. These people are trusted with the producer's data. They're in contract to do something with them. But then there's this third box here, and this is like a service provider, like your internet service provider. They're providing LoRa. They're not really necessarily trusted, and they're often deployed as cloud. So this is just simple software. It doesn't need to be running anywhere. As long as we have a good link, good internet link between the software and the actual gateway installed in the environment, then these can run anywhere. We can do downlinking too. For example, let's say this application out of the blue decides it needs to send a message to a sensor. Let's say a user said, turn on the irrigator. Then it can send without any sort of connection, it can just send on a packet to the application server saying, please send this to the device. And then similarly to a response that packages it up into a LoRa packet, the network server decides which gateway to ask, and the gateway sends it to the device. So we can kind of do both ways. Keep in mind that LoRa is designed to have a lot less downlinks as there are uplinks, but it's still completely possible. Okay, then the last thing was encryption. And this comes back to the idea that this service provider here may not be fully trusted by the device owner or the trusted vendor. So LoRaWAN has created a way for the service provider to carry your bits without being able to, with the service provider, in a way that the service provider can't read your bits. This is similar to, say, you going to your bank's website, your browser doing HTTPS, encrypting your data, asking your internet service provider to get it to the bank's servers, and then the bank servers decrypt it. That internet provider in the middle couldn't read any of the data. Good thing is LoRaWAN has all this built into the standard. In fact, there are actually 2 different keys. There's one called the application key. This is the encryption key that's used to encode the data that the sensor creates. And it stays encrypted all the way until the application server when it gets to the trusted vendor where it can decrypt it. But there's also a sessioning key, which encrypts and validates messages at the network level. This allows the service operator to know that the device that it knows and trusts is the one sending the message, and it allows it to securely communicate network commands. And like we said before, these 2 things together essentially make it so that you don't have to trust your service provider. You can just pay for service like you are paying for cellular service or like you're paying for internet service at your farm. But you have to ask the question is, how does a service provider do business? They need to be able to control who connects to their network so they can charge for it, right? Because if they don't have a business model, there's no incentive to build the network. Well, this is accomplished in LoRa through joining. Joining is a sensor requesting to join and participate in the network. A request looks like this. The sensor sends a join request to the gateway. The gateway sends it to the network server because it's just blind and always does. And the network server sees that it's a LoRaWAN control packet, so it sends it to the join server. It ensures that it tells the join server that it's a valid packet. Then the join server then looks at it and decides, do I know this device? Is it okay to let it connect? Maybe some business questions like, does this account have enough, is it paying enough to have this many sensors or so on, however the network is being sold. Let's assume that the join server approves the request. Then what happens is the join server sends multiple messages. One of them goes to the network server and it says, hey, that device is allowed and it should be sending its data to this application server. And so the network server just remembers that. It also sends some keys. It sends both the network key and the application key, the session key and the application key to the device. And it sends just the application key to the server. And then finally, the gateway sends both keys to the device. Now, everybody knows their keys. The LoRaWAN network knows the session key, the device and the application server knows the network key, the application key, and we can have our secure private transport of data. You might be wondering, wait, if the join server made both keys, then the service provider knows the encryption key. Well, thankfully, there's a technique in encryption that allows you to not send the keys, but send a few pieces of data. And that pieces of data then can be used by this side and this side to compute a key that they both share in secret, but it's not enough for anyone in the middle, including the join server, which created those pieces of data to create the key. So it plays this arbiter to get the right data to the right ends, but they privately compute the encryption keys. All this combined essentially means a service provider has a business model. They can deploy a network. They can charge device owners per the number of devices they connect or the number of messages that they send. They can charge they can charge the vendors and users on the other side for access to their network to get data through it. This is a healthy thing, and it means that there'll be a service provider in the middle that will invest and deploy all these gateways throughout rural America. The last few things I want to just show you some cool outcomes of LoRaWAN's design. You can have a lot of gateways per network server. And there's some advantages for doing it. Say, for example, this sensor sends a message, and in this case, all three of these gateways receive the message. Then all three will blindly send the same packet to this network server. The network server notices, it deduplicates it, and sends only one to the application server. Oops, excuse me. And that way the rest of the network thinks it only sees one message, even though three were received. The advantage here is, let's say there was an interferer that made this link not work. Well, instead of having to notice that, then send back a message to the sensor and say, hey, we didn't get your packet, can you send it again? And then have it send it again, so two extra requests, it's possible that one of these other gateways received it and got the packet through. So because of this design, if you have sort of an overlapping network where one sensor can see multiple gateways, it becomes a lot less likely that a sensor would ever have to retransmit data, even amongst noise and interferers, which ultimately saves a lot of power. There's also this fun fact that if you have enough gateways hear a sensor, some LoRaWAN implementations can do some rough triangulation to figure out where it is on the Earth. This is really useful when you need to go find a specific sensor, but you've installed 300 of them and you don't know where that particular one is. It can help you find it on the ground. You can also have many application servers. So this device might send up its measurement once and it gets to the network server. The network server sees, oh, there are two different applications and 3 different end users that need it. And so it duplicates the message and sends it to everybody. That saves this sensor having to send it 3 different times. It can send it just once and all 3 endpoints get it. So again, it saves a lot of transmission. You've got downlink actuators, which work something like this. We already talked about downlink a little bit, but when they come through, this LoRaWAN network, now that there are multiple gateways, uses its history of receiving data from this sensor to decide which gateway is closest or which one had the highest receive power. And then it asks that one to send the data on to make sure that, to increase the chance that it gets there. So that's how downlinks are handled when you have multiple gateways. And with that, we could talk all day long about a lot of these things, and we could dive into a lot of these really cool waveform ideas that make LoRa really successful. But I think I'll stop for now, and we can do that on another day, and pass it off to Jack Stucky from WIN. He's going to talk about how WIN is, what WIN is doing in the region, and how they're trying to deploy LoRaWAN to solve their problems. And he's got some really cool show and tell to show you some of the real hardware that's out there. So with that, Jack, it's all yours.
Thanks, Andrew. Some of you may know what WIN is, but for those of you who don't, I just want to review quickly. WIN, Wabash Heartland Innovation Network, is a not-for-profit 501c3 formed 3 years ago thanks to the incredible generosity of Lilly Endowment. WIN is comprised of 10 counties in northwest Indiana, with Purdue University and Ivy Tech situated in the center. In our 10-county region, agriculture and manufacturing are our 2 major industries. For the first 2 years, we've been primarily focused on IoT technologies in manufacturing and ag. Specifically, we've been focused on the T, In the last year or so, we've realized that we need to help accelerate and innovate on the I of IoT. So, we bought an aerostat. The aerostat is an 80-foot long tethered blimp that flies between 1,500 feet and 2,000 feet high. It has a payload of 300 pounds. Our charitable mission is around research and education, so deploying a novel rural broadband solution fits nicely. In addition to the uniqueness of the aerostat, we also chose to deploy a new fixed wireless broadband technology called CBRS in partnership with Watch Communications and RTO Wireless. And to stay true to our goal of IoT in ag and manufacturing, we'll also be deploying a LoRaWAN network from the aerostat. The current estimate is that we'll be able to get sensor data from farms and factories as far away as 50 miles. Again, we intend to empirically determine the actual propagation and reliability of hosting LoRaWAN at 1,500 feet. In addition, 10 LoRaWAN gateways will be deployed on traditional terrestrial assets, one in each of our 10 counties, providing a unique opportunity to have a 70 by 90 mile LoRaWAN network. We expect quite a few challenges in the next 3 to 9 months, and we hope to deploy additional gateways as needed. Some of these will be private, and others will be public. We're also trying to see where all the different LoRaWAN players, such as Senate, Things Network, and others fit in. Can they all interoperate, or will we have to make hard choices? Next, I'd like to take a few minutes to show some different LoRaWAN hardware that we're getting ready to investigate. First, I'll show you a LoRaWAN gateway from Multitech. This is an outdoor unit that can be deployed on an antenna tower or on an aerostat. It has built-in GPS and cellular capabilities. Next, I'll show you the granddaddy of the LoRaWAN. Currently, this is on a test fixture. This is a Tektelic Kona Mega. It also has built-in GPS, and it uses 2 antennas, and this will be what will be deployed on our aerostat. Next, I'm going to show you a few of the IoT clients, LoRaWAN clients. This is a soil moisture sensor from Tektelic. The 2 probes put in the ground, and then it can communicate to LoRaWAN gateway. Here we have another Tektelic soil moisture probe. It uses a standard watermark probe for its sensor readings. Then we have a Tektelic gateway, or Tektelic GPS tracker. This is a self-powered unit about the size of, a small bread box. And it's meant to go on top of assets such as semis, other types of assets that are out in the field. Here we have a LoRaWAN to industrial connector. It can sense a variety of different input digital signals and voltages, and then sends it back via LoRaWAN. One of the things that we're very interested in is, some of you may know that we have a very large weather station network. Currently, WIN, in partnership with Co-Alliance, has over 150 weather stations deployed in our 10-county region. Today, those weather stations use 3G networks, cellular 3G networks, to send their data back to the cloud, and we'd like to replace that with LoRaWAN. So to give you an idea what that looks like, here is an example of our current Davis weather station. You can see the top here communicates to the cellular unit in the middle, and the cellular unit also communicates with our soil moisture temperature unit at the bottom. So we'd like to replace the cellular portion with a LoRaWAN solution. We've actually engaged in a proof of concept project with a company called SolChip. SolChip makes a standalone LoRaWAN solar-powered device that can interoperate with a variety of different types of interfaces, and so we're going to be deploying a proof of concept using this on our weather station. So where do we go from here? One of the things that we do know is that LoRaWAN is gaining in popularity, and while it may not be the end-all be-all for a low bandwidth network, the deployment costs are fairly reasonable, and we are going to learn a lot more in the next 6 to 12 months. And one thing I would ask for everyone is that if you have a project that needs low bandwidth data in our 10-county region, please reach out to us. We'd love to work with you on your next project, and potentially can put you on this 70 by 90 mile network. Thanks for having me today.